Alrighty, so this is our 6.1 homework review here, starting with number 19. Basically, when we're looking at this, I'm given some information. Here is a diagram to go along with it. And what we are saying is that we've got circles O and Q, and they have a common chord AB. So AB is part of O and is also part of Q. The next thing we're looking at is if AB is 6, and circle O has a radius of length 4, and circle Q has a radius of length 6, how long is OQ? So my goal here is to try and figure out the distance between O and Q. So doing this, I want to fill in the piece of information I get first, which is that AB is 6. So as I look at this thing here, from here to here is 6. Now I'm going to also label some information, which is that O has a radius of 4. If O has a radius of 4, any point like from O to A or O to B is also going to be 4. Cool. Let's see here. We also get our circle Q, which has radius 6 and 6 as well here. So I'll probably draw a bigger picture of this below just so we can see what we're looking at. But we're trying to find the distance from O to Q. That's my goal. So as I look at this thing, it looks like I have a triangle which is created. Let's use orange for OQ. And then I've got this one here. This we know is 6. This
Wait,
we know
how
is
is
4.
A to Q 6?
Because Q has a radius of 6.
Oh, okay.
So all these distances from Q to B and Q to A are both going to be 6. Good question. I'm going to draw an altitude down here. And then I'm going to draw the other half of it here, but just like as illustrative purposes. So it would be nice to name this point here. It doesn't really need a name, but let's just call it X. Okay, so X is the intersection between AB and OQ. So now as I'm looking at this thing, if I have a chord and a chord being intersected like this overlap, the distance out's the same, distance out the same, well, what type of triangle did I just end up creating? I just ended up creating, whoops, let's get the green here. So I just ended up creating an isosceles triangle. So if I created an isosceles triangle and I dropped my line down like this, how is it going to intersect with the base? It's going to intersect at a right angle. So as I look at this thing, here I've got a right angle, here I've got a right angle, and now I'm going to be able to figure out what this is based off the fact that I just bisected this chord. So what used to be a full 6 is now going to be 3 and 3. So now as we look at this thing again, if we intersect a chord perpendicular, then it's going to bisect the chord. That's something we learned yesterday. So now just focusing on this triangle here, I should be able to figure out this length between O and X, and then I should be able to, just focusing on this triangle here, figure out the distance from X to Q. So let's do that. We'll focus on this one first. So I'm just going to draw my right triangle. This one's 4, this one's 3, there's my 90. What's a variable we never use? We never use R. So we're going to use R here. R squared plus 3 squared equals 4 squared. Subtract off 9, subtract off 9. So 16 minus 9 gives me 7. So R would be plus or minus root 7, but we can't have a negative length, so it's just going to be the positive one. I'm going to say this distance here is square root 7. And now I want to do the same thing for this triangle. Do it in pink. Here again we have 3. Now we got 6. Let's use W. W is a fun one. That's not an awesome W. That's a better W. So looking at this here, again, same setup. 3 squared plus W squared equals 6 squared. Whoops, that's not a 6. There we go. So basically I've got w squared equals, so 36 minus 9 is 27. Now here I'm going to take my root. Again, it's going to be positive. So w equals square root of 27, which we're going to simplify to 3 root 3. So I've got 3 root 3 here, and I've got root 7 here. So my final answer for like OQ, in terms of what I'd be looking for the final answer here, would just be OQ equals square root 7 plus 3 square root 3. And I am good to go. Any questions on this one? Perfect, perfect. Let's go down to 23 here. So here we're considering a circle or congruent circles. Explain why each statement is true. So in terms of like explaining these things, I'll talk through it quickly with you. It doesn't need to be like a super long in-depth thing. I'll give you kind of like a formal answer for each, but also just kind of like talk through. So let's do A here. So the first one we'll do, so congruent arcs have congruent central angles. Well, anytime I'm given a arc, it is the same measure as my central angle, and that's by definition. So really, if you wanted like the super long version, we'd say something like the measure of an arc equals the measure of its corresponding central angle, therefore congruent arcs have to have the same congruent central angles. Like something along those lines would be what we're looking for here. Let's do the next one. Congruent central angles have congruent arcs. So this is essentially the same exact thing we just did, but now in reverse. So if I had an angle which is the same here, I'm going to say their arcs are going to be the same as well. So again, if you wanted like a super long version, the measure of a central angle equals the measure of its intercepted arc. Therefore, congruent central angles have congruent arcs. Pretty straightforward. Next one here we'll do in green. Here we get congruent chords have congruent arcs. So this one's a little bit more interesting. So I'll draw a chord like that and a chord like that. So I'm saying the length here is the same as the length here. So I'm saying that this one is the same as that one. So in terms of like doing this, basically we want to draw radii to the endpoints of the congruent chords. So let's say got my radii out here and a radii out here, radii out here, radii out here. And then from here, the two triangles formed are congruent by side, side, side. So again, basically all my radii are the same. So like double tick, double tick, double tick, double tick. Oh, come on. There we go. So I got two congruent triangles side, side, side. Therefore, all their angles are going to be the same. So this central angle is equal to this central angle. And just like the one we just did before, if the central angles are the same, then they have congruent arcs. Let's look at D. So here, congruent arcs have congruent chords. This is the reverse of what we just did. So what you're basically going to start out with is just the opposite and work your way back. So here, this thing is equal to this thing. Do the same thing where we draw our radii out. So radii, 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 cool. And now I'm able to get from this squiggle that this angle is this angle. Again, I now can say I've got side, angle, side similarity. And then from there, I'm able to say they're two congruent triangles. If they're two congruent triangles, I can say their sides are the same. I can do whatever I want. So corresponding parts congruent triangles basically says the chords are therefore congruent. So be talking about that length there and that length there.
Will we have to like do something like this on a test?
If it were on a test, it would be looking more like this probably. I'll give you a chord like this, a chord like this, and a chord like this. I would tell you this one's 80 degrees, 80 degrees, I don't know, 70 degrees. I'd say this is X length. I'd say this is 10, this is 9, and I'd say tell me what X is. and you should be able to tell me it's 10. Does that make sense?
Yeah.
Cool. Yeah, that'd be kind of like the practical application of it. So less of like the needing to prove this thing is more of like need to be able to use it. Congruent central angles have congruent chords. So this is basically what we've just shown already. If I've got a central angle like this and some other one over here like this, then what I'm looking at is again 4 congruent radii. So if my radii are the same, then I'm able to say the triangles that would be created here, hence the actual chord itself. Triangles are going to be congruent. If they're congruent, then their parts are congruent, and boom, I get the chords are congruent. Last one. Congruent chords have congruent central angles. So again, kind of already going off of one we've looked at here. Congruent chord, we showed, has congruent arcs. So if I've got congruent chords have congruent arcs, and arcs are the same as central angles, then I've already shown this. So it's the same idea, just now I'm giving you congruent chords to start. So I'm basically starting out with this and this, and then from here, you would draw out your whole, 4 radii. Okay, these 2 triangles are congruent. Okay, what can I say about them? They're actually the same. Okay, therefore their central angles will be the same. Or you could just jump right to central angles. Any questions on this one? Perfect. Next one here is 25. So this is kind of the fun clock problem. It's funny because this one, people will think that 6:30 is the same, and so they'll say there's 0 difference, but they're forgetting the fact that because it's 30 minutes, that the 6 has moved halfway between the 6 and the 7. We could actually figure this one out just by like logicking our way through it. All right, here are my 2 clocks. Let's get an approximate. So I'm going to say this is my hour hand at like 6, and there's my minute hand at 30. Put my hour hand at 5, minute hand at 40, something like that. So there we just have our 2 clocks here. So to represent the distance on this first one, again, I'm always starting at like 12 o'clock, which is my straight up and down. And from here, how far have I gone for my hour hand? So for the hour hand, basically, because I'm looking at the angle formed between the 2, so it's just going to be the difference. When I'm looking at the hour hand, basically I'm saying, okay, well, how many hours do I have? I have 6 1/2 hours out of a total of 12 hours. And I would say times 360 is going to give me some degrees. And then for my minute hand, I would do the same thing. And for my minute hand, so this is minutes, and it's going to be my 40, oops, minute hand's pretty straightforward. So 30 out of 60 minutes times 360, my full circle, gives me 180. In terms of my 6.5 out of 12 here, let's see, gives us 195 degrees. And so now I'm looking for the difference between these 2 things. So now I'm doing 195 minus 180 to get 15 degrees. Now as we look at the next one here, so this was my hour hand. I'm going to set the same thing up. So I'm going to do my hour hand in orange here as it comes around to here. So for my hours, oops. So for hours here, we have 5 out of 12 plus, and now for my hours here, it's not like as cut and dry because 30 is 1/2 of an hour. So now I'm just going to call this 40 out of 60. If you wanted to call the last one 30 out of 60, that would have been totally fine as well. I just kind of like jump to the fact that we know that 30 is 1/2 of an hour. So sorry if I didn't explicitly say that. So here now for our hour stuff again, times 360, which is my full circle. So let's do our 5 and 2/3 times 360 here, which gives us 5 by 12, 170. And now we'll take a peek at the minute hand. So starting coming around all the way to here. So for our minutes, we have 40 out of 60 times 360 equals 240. So now I'm just going to be doing 240 minus my 170. So that's going to be my final answer of 70 degrees. Whoa. There we go. Good to go. So we're saying this angle in here is 70 degrees. And we're saying this angle in here is 15 degrees. If I can get a little angle in there. There we go. Any questions on this one? Perfect. I would say this is a good time to stop. See what I did there?